our next section of work, we're going to be looking at numbers and functions, which will involve a bit of curve sketching and all sorts of things. So let's start off with, well, real numbers, which are basically all the numbers that you've been working with now for, well, quite a few years. Prime factors. The prime numbers are the building blocks of all our integers, if you like. They'll all be broken down to its prime factors. So every, well, what we call natural numbers. Let's have a look at 324. 324 is 4 81s, but we can keep going because they're not prime. 4 is, of course, 2 squared and 81, 3 to the power of 4. So it is as a product of its primes. Highest common factor then. The highest common factor. How you work it out? You get two numbers, you want to work out the highest common factor. You write them down in terms of its prime factors. Then you take out the common factors. So let's have a look. 1176 and 252. So 1176, that's 6 196s. 3 times 2 times 49 times 4. So we get 3, 2 cubed, 7 squared. 252, that's 4 63s. 63s are 97, so we get 2 squared. So the highest common factor, we pull out the common factors, the things they have in common. This basically is the same in algebra as when we're just simply factorising. You do exactly the same thing. So before you looked at algebra, you did actually factorise, hence where the word comes from. Because it's basically pulling out prime factors. Well, in algebra, they're algebraic factors of what we get. So we get the lowest power. Of course, whenever you're factorising, you always pull out the lowest power. So 2 squared, 374. So it's the same. Whenever you're factorising, you're taking out the lowest power. Doesn't matter whether it's algebra, whether it's prime factors, it's the lowest power they have in common. As opposed to lowest common multiple, which in algebra, lowest common multiple would be the same as, have a think while I pull this out. So again, we would write them as the prime factors, but to work it out, we write down all the factors without repeating. Well, what did we do that with before? All right, well, let's do an example. So I had a simpler one here, just 48 and 15. 48 we know is 16 threes, so that's 2 to the power of 4 times 3. 15 is just 3 times 5. So the lowest common multiple would be 2 to the power of 4 times 3 times 5. Exactly, yeah. It's the denominator. I don't write the 3 down again. If it's not there, put it down. It's the same idea. So in fact, when we're finding that common denominator, we are in fact finding the lowest common multiple of the two algebraic expressions. We're doing exactly the same thing. So 240 in that case. All right, divisibility tests always come in handy when you're, certainly if you're doing things like solving quadratics and you want to, oh, hang on, does this go into it and so on. If you know these divisibility tests, you can sometimes save a bit of time. Divide by 2. If you're getting quick, you can have the easy one first. How do you know if a number is divisible by 2? There you go. So it's an even number. 3 we talked about the other day in one of our problems. Right? So all the digits add up to be a multiple of 3. 4. Right, it's all to do with the last 2 digits. So last 2 digits divisible by 4. Again, if you're getting quick, 5. All right, ends in a 5 or a 0. 6. Yeah, all you do with 6 is you combine the 1 for 2 and 3 because they are the 2 prime factors of 6. So it satisfies 2, it satisfies 3, then it must be divisible by 6. 7 is a tricky one. Does anyone actually know 7 without having to look at the sheet? Okay. Double the last digit, subtract it from the other digits, and the answer should be divisible by 7. All right, so double the last digit, subtract it from the other digits. All right, now just subtract it from the other digits. So, like, let's get a number divisible by 7. Is that what we had up there? Both of you said 243 very quickly there. 343. Okay. 343. Double the last digit 6, subtract it from the other digits. 31 minus 6 is 28. 28 is divisible by 7. So therefore 343 is divisible by 7. So, yeah, that's the one people often don't know, that one. They think, ooh, 7, you can't do 7. All right. Well, even if you didn't know 28 was divisible by 7, you could still do it. Because you double 8, you get 16. Subtract it from 2, negative 14. 14 is divisible by 7. But if you didn't know 14 was divisible by 7, you double the last digit, which is 8, subtract it from 1, you get negative 7, and hopefully you would know 7 is divisible by 7. So you'd be right. All right, 8. Well, no, you can't do 4 and 2. Because 4 and 2 are built from the same number. So you can't say 4 and 2, because as soon as it's divisible by 4, it's automatically divisible by 2. So 8 actually is, you now play with the last 3 digits. And the last 3 digits is divisible by 8. 9. Yeah. So it's similar to the 3 one. Some of the digits divisible by 9. A 10? Oh, good. Ends in a 0. Now, you were onto something before and you thought it was 11.
I think it was like every alternate digit you added and then you subtract it from the remaining middle digits, and then if that's divisible by 11.
I think what you're saying is it. So you get the digits in the even position, you get the digits in the odd position, and those sums, if they differ by a multiple of 11, it's divisible by 11, yeah. So I think that's what you were saying. Yeah. And I think I stopped there because it looks like I haven't got any room left. But I mean, there are tests for 12 and 13, and away we go. Okay. Fractions and decimals there, that's integers. But then, of course, we broke integers down. I mean, maths is like that, and we always lie to you, basically, so we can do maths. You ever notice that? So like back when you were in like infant schools, the only numbers that existed were positive whole numbers, and life was great. And then you said, well, hang on, 5 minus 10. Can't do it. Can't do it. Oh, what about 2 divided by 3? Can't do it. And then maths became real easy because it was just can't do it. But then we upped the ante bit and introduced new families of numbers, and fractions and decimals came into it. Now, converting fractions into decimals, very easy, because it simply is a division. That's what a fraction is. It's a shorthand way of writing down the division. 2/3 is 2 divided by 3. So you just do the division. Going the other way can sometimes be tricky. Now, if it's a terminating decimal, again, very easy because of the decimal system that we use, base 10. And so we know the first spot is tenths, then hundredths, and so on. But if it is not a terminating decimal, well, if it's irrational, then obviously we just can't do it. But if it is rational, so a recurring decimal, so converting recurring decimals into fractions, the traditional way, I'll show you the traditional way first, and then I'll just show you the way most sensible people do it after that. Because the traditional way is long, but again, it's all about discovering patterns. Start with ones we can work out, I hope. 0.6 repeater. Oh, good. 2/3, okay. So traditionally the way we do it is say, 0.6, that would be 0.66666666666, and it just goes on forever. And so I say, okay, well, let x equal 0.6 repeater. So x is 0.66666, and so on forever. And then I'll multiply it by 10 and get 6.6666666. But I've got simultaneous equations, and I can subtract the bit that's annoying me, that long repeating bit, and I get 9x is 6, so x is 6/9, and so there we go, 0.6 repeater is 2/3. So that's the traditional way of doing that. And if it was 2 numbers repeating, we did a similar thing. So 0.81 repeater, 8188181818181818, and so on and so on and so on. We'll let x equal that, But this time, instead of going 10x, because if I went 10x, it's no good. Because I've got 0.81, 81, 81, 81. If I went 10x, then I'd have 8.18181818. They don't line up and I can't subtract. So I've got to multiply by however many numbers are repeating that 10 to the power of that. So 10 to the power of 2 or 100. That gets the repeating part lining up. And we get 81 over 99, which of course simplifies down to be 9 on 11. Okay. And then we have ones where not all the numbers repeat. 0.327, but only the 2 and 7 are repeating. So 0.3, 27, 27, 27, 27, 27, 27, 27. So we'll let x equal that. Again, there's two numbers, excuse me, there's two numbers repeating, so I'll multiply by 10 squared or 100. So 100 and x would be 32.7, 27, 27, 27, 27, 2. The 27 bit cancels, and I get 32.4 over 99, but that's a bit messy. We don't normally have decimals on fractions, so we can multiply top and bottom by 10, and we get 324 and 990, 18 on 55. But as I say to you, that's the long way of doing it. The quick way of doing it is just looking at it and writing it down. 0.6 repeater. Well, I know 6 is repeating, so I'll put that on the top of the fraction. 6, because that's the number that's repeating. Bottom of the fraction, I'll put 9, because one number is repeating, so I'll put 1 9 down. Bingo, that's it. That's all you're going to do. So 0.4 repeater, 4 ninths. 0.2 repeater, 2 ninths. 0.9 repeater, 1. Easy. 0.9 repeater is 1. We did know that, didn't we? Yeah. Well, the reason 0.9 repeater is 1, because tell me the difference between the two.
You never know.
Well, exactly. So it's going to be 0.000000000. Well, so if you're only subtracting 0, it's got to be the same, isn't it? Okay. 0.81 repeater. Oh, 81 goes on top because that's what's repeating. 81, 81, 81, 81, 81, 81, so 81 goes on top. 99 goes on the bottom because two numbers are repeating, so I write down 2 nines. Now, I don't write down 18 because that's 2 nines. I physically write down 2 nines. So anything where there's two numbers repeating is over 99, so 0.46 repeater would be 46 over 99, and so on and so on. 9/11ths. So if I had 0.7134 and all the numbers are repeating, then the answer is 7,134 over 9999. We don't have to do this long piece of algebra. We can just look at it and go, that's the answer. Does that simplify? Oh yeah, of course. I'm sure you spotted that. 2378 over 3333. What about the one where not all the numbers repeating? This is how we get the top. It's 324 on top. 324. Why? There you go. 327 is the number. But I subtract 3 because it's not repeating. It's not part of the repeating. Yeah? So I write down the number 327, but I subtract the number that's not repeating. That goes on top. On the bottom, 990. Two numbers are repeating, so I write down 2 nines. One number is not repeating, so I write down 1 0. How do I know to put the 0 at the end? Well, because if I put it at the front, then it's not going to change the number. It's going to be 99. So it's got to be at the end. Yeah. So if I had 0.1096, but only the 96 are repeating, before today you might have gone and done some long calculation. But now all you've got to do is that. 1,086, because that's 1,096 minus 10, over 9900. Two numbers repeating, two numbers are not. 9900. There's our answer. That simplifies down, by the way. 181 on 1650.